Okay, now we are in section 7.3, mean confidence intervals. So we're going to focus on constructing a confidence interval. For a population mean, mu. But we have two cases here. And the reason is that our differences in constructing a confidence interval is actually quite significant when we either have a population standard deviation, sigma, that's given, or we have to estimate it using the sample standard deviation. So when we use the sample standard deviation, as we'll do in this video, we introduce additional variability and error in the estimate of mu. So our sampling distribution that we're using in this construction is not normal, but in fact we have to use the student t distributions. So we're subject to we have a underlying distribution is normal. Maybe it's not. This construction works fairly well regardless of this condition. We have either n is greater than 30, or we might not have this, in which case we'll introduce quite a bit more variability. And the third condition is that we estimate the population standard deviation sigma with S. So in probabilistic language, what really is happening is, if we're thinking about both mu and sigma as unknown, we're using a random sample to extract actually 2-point estimates. So the first being x bar, the sample mean, and the sample standard deviation S. So S is the point estimate for sigma, x bar is the point estimate for mu. And both of these things are happening simultaneously, but we're actually interested in is estimating mu ultimately. And then, of course, we're given a confidence level 1 minus alpha. So this determines how high our confidence is that our point estimate is giving us a good approximation for the parameter that we're approximating, which is in this case mu, and that mu, the parameter, actually lies in this interval. So given this, we have a procedure that will give us a confidence interval where the margin of error, E, is given by t sub alpha over 2 times S, the standard deviation from the sample, divided by the square root of n. So what's actually happening here? This is a critical student t distribution value coming from the student t distribution with degrees of freedom equal to n minus 1. And what this critical value is actually giving us is, if we can imagine that we have the sampling distribution of x bar, we have this slightly fatter bell curve where, again, the student t distributions have 0 as a mean, but they have a higher variability than the standard normal distribution. And what t sub alpha over 2 is giving us is alpha over 2 is the area in the tail, the right tail specifically, for this distribution. And then similarly, we get a negative version of this that is giving us the lower alpha over 2 in the tail. So when we're talking about this in precise terms, when we're actually looking at an example, alpha will be something like, say, 0.10, right? So in other words, in that example, we would be looking at, if we had a, say, 90% confidence, then we'd be looking for t, so alpha is 10%, right? Or 0.10, which means we're looking for t of 0.05, which means that there's 0.05 in the upper and lower tails. So what is all this good for? What we're saying then is this construction, which we might also call a t-interval construction, is giving us a confidence interval for our population mean. So we're saying the population mean lies between the lower bound and the upper bound of this confidence interval, which is the point estimate. Whoops, that's a really ugly looking X bar, which is the sample mean plus E, which is t sub alpha over 2 times s over square root of n, and X bar minus t sub alpha over 2 times s over square root of n. Okay, so again, as before, this is the lower bound of our confidence interval. This is the upper bound of our confidence interval. And this kind of a confidence interval can be written as X bar minus E, comma, X bar plus E in interval notation. And so this is actually an example of a symmetric confidence interval. So if you're using a TI-84 or any of the cousins of the TI-84, you will be using a function called t-interval in the tests menu. So look for it in tests. And what this function will give you is the margin of error. That'll give you E, which means you'll have to actually construct the interval using the interval notation directly by taking the point estimate and the margin of error and taking plus or minus E. So remember that this is the method that we use if we are not given the population standard deviation and we have to estimate it using S, which introduces error, and the sample size possibly is larger than 30, but also might not be. This is actually a pretty robust construction.